Good afternoon, everyone, and thank you for coming. My name is Megan Malia, and I'm the chair of the Dean Scholars Distinguished Lecture Series Committee. Dean Scholars is a research-oriented honors program in the College of Natural Sciences. We have been welcoming remarkable scientists to UT to share their groundbreaking research through the Distinguished Lecture Series for the past 20 years. It is truly an honor and a privilege to introduce you to our 2019 Distinguished Lecture Series speaker, Dr. Rainer Weiss. Born in Berlin, Dr. Rainer Weiss received both his bachelor's degree and his PhD from the Massachusetts Institute of Technology. He returned to MIT after serving as an assistant professor of physics at Tufts University and then as a research assistant at Princeton, and has been at MIT since 1964. As an experimental physicist, Dr. Weiss has contributed to a variety of fields, including atomic physics, laser physics, and astronomy. In his career, he has primarily focused on two phenomena: cosmic microwave background and gravitational waves. The focus of today's lecture is on gravitational waves, which were first predicted by Albert Einstein in 1916 in his theory of general relativity. Nearly 100 years later, in 2015, the LIGO collaboration, which Dr. Weiss helped found, observed gravitational waves for the first time. Since then, Dr. Weiss has continued to make immense contributions to the study of gravitational waves, which have been said to be an entirely new way of observing the most violent events in space, such as the collision of black holes. Dr. Weiss has been awarded the Einstein Prize, the Special Breakthrough Prize in Fundamental Physics, and the Kavli Prize in Astrophysics. He has also twice won the Gruber Prize in Cosmology. Most notably, in 2017, he was awarded the Nobel Prize in Physics for his contributions to the LIGO detector and the observation of gravitational waves. In a brief history of time, the late theoretical physicist Stephen Hawking says, "We find ourselves in a bewildering world. We want to make sense of what we see around us and to ask, what is the nature of the universe? What is our place in it? And where did we come from? Why is it the way it is?" Though we may be a ways from answering those questions, Dr. Weiss's discoveries have helped us get closer to understanding the nature of the universe and making sense of our place in it. One reminder before we begin: please silence your cell phones and refrain from speaking. After the talk, we will have about 15 minutes for questions. Without further ado, please give a warm welcome to Dr. Rainer Weiss.
Thank you. You did wonderful. Thank you. Wow. All right. Wow. Well, I'm very glad to be here, and especially where it's a thing that has been organized by students rather than faculty. I mean, that to me is it's a real honor to be invited by students, I think. And I'm going to tell you about what you just heard a little about, namely about the idea of looking for gravitational waves. I hope I won't bore you. We'll see. And the thing is that I actually am giving this talk, as you can see from the stage, from the view graphs up here, on the behest or behalf of something called the LIGO Scientific Collaboration. Let me tell you what that is. It's a group of about 60 institutions. University of Texas in Austin is now one of those institutions. And Professor Zimmerman, I don't know where you are in this thing, but if you stand up wherever you are, you get known. He's part of this. Yeah. And I can't see anything, so, I just have to trust that something happened out there. And so anyway, that is part of the LIGO Scientific Collaboration, and it consists of, as I said, 60 institutions and about 1,000 people. And here they are. I don't know, and Professor Zimmerman can tell us where to look for University of Texas on it. They may not have been in this long enough yet to have their symbol on here, but it will be if it isn't there now. Okay, anyway, so all I'm trying to tell you is that not just one or two people did this. It was a very large number of people involved in trying to actually measure these gravitational waves and do the science that goes with making the discoveries. So I'm going to start by something which you probably do know. This is Newton, Isaac Newton, and he was the first person to really actually couple some ideas together in gravity, which are really quite profound. One of them is that, yes, apples fall from trees, and that's a famous story, and he associated that with apples, not apples, but the moon falling in the sky. And the fact that association was made, that something on the sinful and very dirty earth should also have something to do with the pristine heavens, was a coupling that was brand new to people in those days, and it became called the universal theory of gravity. And it's most best described by a very simple relationship that many of you may have learned in high school. And what it is there's a gravitational force. That gravitational force is proportional to the mass of one object. Let's say somebody sitting next to you, and then that next person to you, that's another person. That's two masses, proportional to the masses of those two people. But as it gets weaker and weaker, the further apart they are, it gets weaker with the square of the distance. That simple relationship, and there's a constant which can change depending on the units. It's not terribly important. But what that does is it explains almost everything that goes on in the universe. It's very good. It's a relationship that would have been fine. Except it doesn't explain some fairly subtle things, which Einstein later had to correct. And we'll talk about that in a minute. For example, one of the things, it explains beautifully the people going to the moon. It explains beautifully the tides on the earth, all the things you can think of. But it fails in a couple of places. It fails in one place when you start talking about big masses moving with very large velocities, velocities close to the velocity of light. It doesn't work at all. The other thing it fails with, and this is something that Newton probably wouldn't have guessed would have failed the way I'm about to tell you, but people who followed him would have guessed. And that is, if you take the Earth, here's the sun, and here's the Earth going around the sun, okay? And if you suddenly plucked the sun away, what would happen? And what would happen is the following, that you would not notice that plucking of the sun away until about 9 or 8 minutes after it happened. Why? Because it takes light that long to get to you from the sun to here. So you wouldn't notice it right away, but you would notice it eventually. Now, people would have guessed, let's say in the 1900s, or the end of the 1800s, that if you had an orbit of the Earth going around it, and then you plucked the sun away, it would immediately make the Earth go off on a tangent. And that isn't true. It should also take about 9 minutes or 8 minutes for the Earth to realize that the sun had disappeared as a gravitational body. And that was corrected or finally set up properly by using Einstein's theory. And so let me tell you a little about Einstein's theory. There's Albert, much older than he is in that when he invented those equations, but the first thing is these equations. Now you have people right here, like Richard Matzner and others, and Weinberg, who know how to deal with this equation. I'm not so good at dealing with that equation. But I'll tell you what it says. That equation says that the geometry of space and time, which is this thing here, is somehow dependent on the distribution of matter and energy in the space. In other words, the way you make measurements of space and the way you make measurements of time, both are important, are dependent on how you distribute matter in the space. And let me give you a little feeling for that. By the way, it denies entirely the idea of a gravitational force. It doesn't actually exist anymore. So let me see why this doesn't do what it's supposed to do. There it goes. Okay, now I can't see you, but I will shade my eyes. How many of you know what a jungle gym is? Just raise your hands. There are a few of you. Oh, good. Leave the lights on a little bit, okay? I mean, just so I can see what I'm doing. Good. I got to see you guys. And so a jungle gym, of course, every New York kid knows what a jungle gym is. So what it is a whole bunch of parallel bars, and kids jump around in them, but parallel bars in all 3 dimensions. And what's been done here is you've taken a 2-dimensional cut through that jungle gym, and that's what these bars are all around in here. These bars are all nice and straight, but then you plunked into this system the sun, and that makes a distortion in the space. It does something else, which we'll get to in a minute, but most important, in that picture you see the distortion it makes, and there's the Earth making its own little distortion in the space too. And so what happens is that is sort of a symbolic way of looking at what that equation was trying to tell you. You take matter and energy and put it in that space, and it distorts the space. It makes the space look different. So things that were straight lines now turn into curved lines. But there's a much other effect which is not in that picture, which is if you put clocks all along each intersection point, clock here, clock there, all in this flat region out here, and you make them all read the same time at the same moment of time, okay? You have to think how to do that. That's not so easy. Suppose you put clocks all over this thing and put all over there. If you took a camera and took a picture of all those clocks and had a shutter on that camera and took a picture just at one instant, they wouldn't all read the same time. The distant clocks would look a little bit earlier than the clocks near you in that picture. Why? Because it takes time for the light to travel to your camera. So you have to take that into account. That's not what I'm talking about. There is another effect that goes on, namely that the clocks that are here all keep the same time, the clocks way over there all keep the same time, but the clocks in here where the space has gotten curved, they go a little more slowly. And that's the piece that the time gets distorted as well as space gets distorted. And then, and the man who first sort of made a wonderful presentation of that was John Wheeler, who said, yeah, those things that are matter now, that these things that are made of matter and energy, those will be pushed around by the distortions in both space and time. They follow those distortions. And that's the way gravity works. It's a completely different way of thinking about gravity. So, all right, so now let me tell you what a gravitational wave looks like. That fits quite nicely into this. And this is the thing that ultimately this talk is all about. So, first of all, let me say something. Einstein wrote this in 1916. He wrote a paper about using that fancy set of formulae that I can't solve, but people here can solve, and so showing that indeed it has solutions that I'm about to describe to you. And he made a mistake in 1916. We'll talk about that mistake. And he corrected himself in 1918 and did it completely right. And what he discovered was that the sources of gravitational waves are non-spherically symmetric accelerated masses. In other words, the thing that makes these waves, which I haven't shown you yet, but let me at least I'll tell you how they make them. You have accelerated masses, but they can't be spherically symmetric. The source has to be somehow asymmetric. For example, a balloon that blows up and a balloon that collapses completely uniformly will not radiate gravitational waves. But two trains smashing into each other, that'll make gravitational waves. Or one object orbiting around the other object, that's not spherically symmetric. That will radiate gravitational waves. So that's what you want to think of. Accelerated masses make gravitational waves. And what do they look like? Well, they propagate, at least that was Einstein's idea at the time in 1916 and in 1918, that they propagate at the speed of light. In other words, he hypothesized that these waves will travel as fast as light. And by the way, in the middle or toward the end of my lecture, you'll see that we now know that to an exquisite precision. We have real experimental proof of that now, which is a big step. The other thing is that they are transverse waves. Now, let me try to explain what that means. They're waves that do their stuff that waves do. They cause things to wiggle. They do that transverse to the direction, perpendicular to the direction in which they're moving. You're going to see this now. This is going to be a gravitational wave. I'll turn this on. This is a little animation. And there's a little red square there. You may not be able to see that so well, but that's where you're going to be standing, right about there. And I'm going to turn this thing on, and you'll see what a gravitational wave does perpendicular to the direction that it's moving, namely coming out at you. The wave will come out. Let me see if I can make this run. Okay. Yeah, there it goes. Okay, so if you can see the red spot, yeah, there it is. That's you. Not much is happening. I've sprinkled masses around, little tiny masses that shouldn't cause too much trouble. And I've sprinkled them around, but you'll notice some interesting patterns in this picture. The first thing you'll notice is that in one dimension, this is now, let's call it the x dimension, the space is expanding while it's contracting in the y direction. And the z direction is the direction the wave is going in. So perpendicular to the direction in which the wave is moving, it's expanding space in one dimension and contracting in the other, and it's oscillating. It keeps changing what it's doing. You'll probably see that back and forth. That's one attribute you'll see. So you get this very interesting thing. You get pulling of space in one dimension, compression of space in the other, and it keeps flipping back and forth. That's going to play a big role in how you detect these things. The other thing that's important in this is you'll notice that there's a lot of motion in the here you are again, a lot of motion in the places that are far from you, like this mass and that mass. They're moving a lot, but the two that are close to you are not moving much. And so the amount of jiggle some amount of space does is proportional to the separation of the points in space. The bigger the separation is, the bigger the motion is at the endpoints. You got that? And that is a strain. When you say something wiggles, the delta L, the amount it changes, delta L, is proportional to L, which is the separation. Delta L over L has a name, and we'll talk about that more. That's called the strain. And for example, you could prove, if you want to do this for yourself, it's easy to show and get motions that look like this by taking a rubber band, and at least you do it in one dimension. Get a rubber band, get a friend of yours holding the rubber band, and make marks every eighth of an inch or on the rubber band, and then stretch it. It looks just like what you see here in one dimension. You'll see exactly, and that is, as you pull it, a motion of constant strain. If you pull it, and you'll see the strain is the same everywhere you measure it along that piece of rubber band. Okay? So you have strains that are positive in one dimension and negative in the other, and they keep flipping back and forth. So the big thing is to measure that strain. And so now you have an image, at least, of how one might go about detecting these gravitational waves. Now, the first people to actually get into the business of measuring gravitational waves, and they didn't know they were going to get into that business, is Russell Holt, who was a graduate student at the University of Massachusetts in the 70s, and his professor was Joseph Taylor. Now, they both wound up at Princeton after they did this, but what they were doing was something fascinating. And they were the first to get some indication about gravitational waves. And here's the thing they were doing. What they were doing is they were down in Arecibo, which is a big dish in Puerto Rico, big radio dish. And Russell Hulse was down there listening to the sky, having pointed the dish at certain places and up, listening to the sky, and he heard a thing going brrr like that. Brrr like that, okay, just like that. And what he was listening to was a pulsar. It's a star that's about the mass of our sun, about equal to the mass of our sun, but about the size of Austin, Texas, not bigger than that. So it's an enormously dense object. The sun weighs, 10 to the 33 grams. I'm going to have to explain 10 to the powers, but it was a very, very heavy object. I'll get to explaining that better in a minute. Huge object in terms of mass. And if you try to pick up a sun that's squeezed into the size of Austin, Texas, and put a spoon into it, you couldn't lift the spoon. There's a density that's so high that you couldn't even lift it. You couldn't try to lift it. So those turns out to be stars that were discovered that oscillate, they roll, they spin, and they happen to a little plasma, they're a little like a searchlight beam that comes out of them, and every time they go around, they make a pulse in a radio dish. And that's what they were hearing. Now, that's what Russell heard. And he heard that, and let's say that the antenna that he had is down here, just like that, and here is the system that was doing it. So he was hearing that pulsar. But he noticed something else, which was very important. He noticed that sometimes the pulsar would go a little more quickly. It would go a little faster, and about 4 hours later it would slow down again. Speed up, slow down. Every 8 hours it went through a complete period. And that told him that this pulsar, which was making these rapid pulses 17 times a second, was sort of living with another star that they couldn't see either of them. No optical telescope could see them, but the radio telescope was keeping track only of that guy who was oscillating so fast, or rotating so fast. And what it was, though, however, a system that was, while they were going around each other, when they come pointing toward the Earth, when they're moving toward the Earth, here's the antenna from the Earth, then it was going a little faster because of the Doppler effect, and then while it was receding from the Earth, it was going a little slower. And that was the effect, and they had this wonderful laboratory, all of a sudden, a laboratory to test general relativity, to test Einstein. And the picture that first described gravitational waves is this one. What they noticed and this is epoch right here, this is time, this is 1973 over there and 2000 over there, and what this is the time it takes for one orbit. He could always tell when he's gone through a complete cycle because it would have gone through speeding up, slowing down, speeding up, slowing down. How long did it take for those things to change? One time, and then they plotted these points, and it's negative here. The thing is speeding up. In other words, the orbit that they're making is getting a little faster with time. And that's what these dots are. These dots right there all are experimental points. And what is thrown through those dots is a curve, which is that solid line that runs through them, is Einstein's prediction for a system that made up of those masses that is losing energy to gravitational waves. And that was the first discovery and the first real measurement of gravitational waves. Namely, by inference, they were able to say, we see this thing as speeding up, they're falling toward each other, these two stars, and they're getting faster, their orbit is getting tighter, and so they're losing energy. And that was plotted, and this curve then was the very first curve ever to show that Einstein's idea of gravitational waves was right. Okay, so that was a very big discovery, and will come back to us in about 2/3 of the way through the lecture. The guy who first tried to actually measure gravitational waves is Joe Weber. This guy. He was an electrical engineer and a physicist at the University of Maryland, and he had a very clever idea. His idea was, he had that picture of the dots that I showed you in mind, and he was thinking, why not make a big aluminum bar? There's a big piece of aluminum over here, and there he is mounting strange gauges on it, little gauges that measure if this bar expands like those dots did, and contracts in one dimension, expands in the other. So contraction up and down, and expansion left and right. He was hoping to see that. And he was mounting these strain gauges, and that whole big bar, which is about his size, winds up in this vacuum chamber and becomes isolated from the rest of the world. And that was his idea, very clever idea. I'd see in Einstein's time, it was you couldn't do a thing like this. The technology wasn't even ready to make such measurements yet. On the other hand, in Weber's time, which is about the 1960s, this was becoming possible to think about. And to Weber's misfortune, and I think I really meant it by misfortune, he did the following experiment. He took one of these bars and had it in his office or near his office in the University of Maryland, and then he had another one on a golf course about 8 miles away, and then he had another one in Chicago near the Argonne Laboratories, the big laboratory near Chicago. And what he had is he was seeing pulses, coincident pulses that were happening at the same time in those 3 detectors. And he kept watching this for some number of, well, not years, but certainly months. And then he published a paper saying he had discovered gravitational waves. And that paper was in 1969. And what happened was, that's a huge discovery. I mean, here was, for the first time, the discovery of Einstein's waves. And so what happens, like what always happens in science, a lot of people read that paper, and they said, this doesn't look so hard, I could do that too. Let's see if I see the same thing that Joe Weber did. And a lot of people did the experiment, about 4 or 5 groups in the United States, several in Europe, a couple in Asia, and to all of our misfortune, nobody saw anything. And that was a big question, what was really going on, what was Weber seeing, and so forth. It was never really quite settled but nobody saw this, and so people began to disbelieve this. And Weber then, in fact, got a very bad reputation out of this because nobody else saw it, and he couldn't really explain why nobody else saw it. So, it turns out, very shortly after that, people who were in that business, who had gotten into this thing, started thinking, well, they think gravitational waves are still worth looking for, but maybe we have to make a better bar. And I'll tell you now that you have to make a much better device than what Weber had then. His system was 1 million times too insensitive to measure gravitational waves now that we have detected them. But that's something he didn't know at the time. Okay, so it turns out a lot of people were thinking what to do next. Some people tried to make better bars by cooling them and making cleverer ways of making the bar oscillate and stuff like that. And there was another group of people that started thinking, why not try to measure that motion of those masses directly? And here's this thing, which is a little animation I'll show you, how the actual detection was made. What this picture is a picture of something called an interferometer. And I'll start it running so you'll see in a minute and get a little better. So you have to identify the things that are in the picture. This doesn't look like a laser, but that's supposed to be a laser, okay? And it's going to put light out to something called a beam splitter, which is this device. That splits the light, so half of it will go through it, and the other half will get reflected. Now, this is something you experience all the time. When you look into a window and the street is well lit, and you look into a window which has not much light, you can look a little bit into it, but you also see your reflection. So the idea that you get light split by something that's a partial reflection is something that shouldn't be a new idea to you. So what happens is that you then take that light, and by the way, this beam splitter, as we call it, is placed exactly at that place in the dotted picture where I asked you to look for the red square. That was you. In other words, that's the red square, it's right there. And then we put mirrors right out where at some distant point in this direction, and another one out there, and then the light will get reflected, come back, come to a detector, which is this thing, which is a little bit pathetic for a detector, but leave it. And so let's get this thing running, okay? So, you'll see where the light is red. Wherever there's light power, it's red. But also, you see the electric field that's in the light. And so you see it being reflected from this mirror, and then you see it reflected from that mirror. It goes to the detector, and if this path length is the same as that path length, no light goes to the detector. Why? It cancels. The two sine waves cancel each other, and you see no red here. Now you come with the gravitational wave comes down, moves this mirror in, moves that one out, and you see when the path lengths are no longer equal, you will get light at that photodetector. That is the whole idea behind the detection that LIGO made. It's no more complicated than that. It gets very tricky to do technically, as we'll see in a minute, but the basic idea of the measurement is no more than that. You set up a system like this and time light as it goes from a beam splitter to a distant mirror and back, and two different directions in the wave, the gravitational wave. And remember, one arm will shrink, the other arm will expand, and that makes it so the paths are no longer equal, and that means light will go to the detector if you set the thing up properly. That's all there is to making this detection. But now comes the trouble. Okay, that's not trouble. Here comes trouble. This is the guy who made trouble. You've had him here talk. I know you had Kip talk, and I think you had Nergis here last week or something. I think you had. Well, anyway, Nergis didn't make trouble. She's trying to fix the trouble. But Kip made trouble. And what Kip said, and there he is about 30 years ago, Kip said, look, if you're going to try to measure gravitational waves and believe something that you see, and here are the symbols that go with this, H, that's called the strain, and here again is the definition of the strain. It's the change in length of the two arms, one goes positive, one goes negative, divided by the distance. And if you're going to make a measurement of that, you have to be able to measure a strain smaller or equal, but smaller than 10 to the minus 21. All right, now I better tell you a little about powers of 10. Now, I'd like to see, how many of you are actually happy with powers of 10? Just raise your hand. How many are unhappy? Well, not that many. Okay, I'll just give one example. You can write 100, for those of you who are unhappy. You can write the number 100 in many ways. You can write it by 100, that's 100, but you can also write it 10 times 10 if you like. And that means it's 10 to the power 2. 10 once times 10 again, 10 to the power 2. That's how you write a big number. For example, a number that's 1,000,000 would be 10 to the 6. Okay? But when you want to write numbers that are very small, you put the numbers in the denominator. So if you want to write a number that's 100th, you have a 1 in the numerator, have the sign between the numerator and the denominator, and then you put 10 times 10 in the denominator. And that, when you bring that up into the numerator, you have a 10 to the minus 2. That's the way that works. And so I'll tell you, I wish the newspapers would use numbers like that. For example, when you read about a budget that's $1 billion, it means entirely different things in the United States than it does in Britain. In Britain, a billion means 10 to the 12. In the United States, it means 10 to the 9. So it'd be much, much better if we can train the public to write all big and little numbers in powers of 10. That's my campaign for the society, okay? All right, so now let's get back to the reality here. What happens is that now you take this and make an instrument that has arms that are 4 kilometers long. That happens to be the length of LIGO, and other detectors are close to that. So the length we're talking about, the denominator here, is 4 kilometers, or 4 times 10 to the 3 meters. And if you now take that 10 to the minus 21 and multiply it by 4 times 10 to the 3, you wind up with a number of 4 times 10 to the minus 18 meters. That is the motion that you have to measure of those two objects at the ends, those mirrors that were at the ends of that interferometer. And what is that number? Well, the size of an atom is about 10 to the minus 10 meters. 10, not 10 to the minus 18. And the nucleus of an atom is about 10 to the minus 15 meters. That's tiny. And you're being asked here to measure something that's even 1,000 times smaller than the size of a nucleus of an atom. And when you talk to an engineer about this, or a sensible person in the world, they'll throw you out. They assume that you've smoked something, Okay? Instead, what it really means, and this is the challenge that Kip threw at us, he says, look, I'll give it to you exactly the way you have to solve it. The delta L you have to measure if you want to make his criteria. And by the way, it turns out his criteria is exactly on the mark, as we'll see in a minute. You have to measure changes in position that are 10 to the minus 12 of the wavelength of light. Light wavelength that your eye sees is around 5 times 10 to the minus 7 meters, or let's call it, for round numbers, 10 to the minus 6 meters. So 10 to the minus 18 is 10 to the minus 12 of that. So that is a first challenge. You have to somehow look at the position of things using light with a gauge that is very much smaller than the wavelength of light. That turns out to be hard, but not as hard as the next one. The next one says, yeah, but if you want to also measure and it means something, you want to get something that means something out of the measurement, you've got to measure something that is 10 to the minus 12 times smaller than the vibrations of the Earth at the surface. Now, what does that mean? You and I, right here in this place, even though we're not that close to the oceans, we are jiggling up and down by a few times 10 to the minus 6 meters, right here. You measure with a seismometer anywhere in this hall or anywhere in your buildings. It's probably bigger than that. Even in the basement of your fancy, your fancy physics building. It's a pretty fancy bit. It's much fancier than what we got. You know, look, you should be proud of that building. It's got, okay? I know you want another building, but MIT doesn't have a building anywhere near as good as one as you have. Okay. So, at any rate, you have to measure Earth motions that are motions of the mirror that are 10 to the minus 12 of the Earth motion, and you have to kill that. So turns out to be the real challenge. Okay, so here we go. So here's the instrument that actually solves the first problem. And this is, by the way, the instrument, and I'll walk you through it a little bit, but not with great detail, and you can ask me questions about it later. But this is the device that actually measured the first gravitational waves. And you'll see some things you already recognize. There's the laser, there's the beam splitter, and there's the distant mirror right there, and there's the distant mirror itself. So that initial parts are all there, but some new things have been added. And one of the new things that have been added, this partial mirror right here. That partial mirror makes this into a device that when you send light into it, it bounces the light back and forth about 300 times before it really gets recombined again with the light. Both things happen on this side. The light goes back and forth 300 times. I'm exaggerating a little bit. It doesn't quite do that, but it's close to that. 300 times in here. But the important thing is the light spends the same amount of time in here as it does in there and comes back out again. And it, again, comes to the situation where no light goes to the photodetector. And all the light, in this case, goes back to the laser. And that's a very bad thing. And I know many of you have lasers in your labs. The laser hates to have light go back into it. It just absolutely rebels against that. So you have to do something tricky, and then this tricky thing is what this mirror is about. And what that tricky thing is what that is a partial mirror again, and what that does is it takes the laser light and reflects it. That's one thing it does. It also, of course, transmits it through, and light coming back to it gets transmitted back to the laser also. So you have two beams here. One beam that hits the mirror, or that partial mirror, and reflects. Another beam that comes from the beam splitter comes through this, and that heads back to the laser. And now what you do is you make those two lights cancel interferometrically, just like they cancel to the photodetector. So they don't go back to the laser. You kill that light interferometrically. And that does something really quite spectacular. What that does is, suppose you have 50 watts of light coming out. Well, we now have 50 watts of light coming out of here. You'll have circulating in this little cavity, which consists of these, something like 10 kilowatts of light. And in here, you'll have something like half a megawatt of light going back and forth. And that solves part of the problem. And now this mirror, which I haven't explained to you, is subtle, and I'll leave it for a question if you want to ask me about it, but I'll tell you what it does. It tunes the interferometer so you can change the way it behaves to a gravitational wave. It allows you to tune the frequency response of the interferometer. That's hard to explain with what you now know. I think I want to start. I don't want to show this because I'm around out of time. So here, then, is the disposition of various detectors, which we'll talk about. These are the 4-kilometer detectors in the United States. There's one in Hanford, that's in the Pacific Northwest. Another one in Louisiana. And then there are other detectors. These are 4-kilometer detectors. There's a 3-kilometer detector in Italy near Pisa. There's a research detector that's 600 meters long in Hanover, Germany, and that has developed a lot of the technology that we use in all of these detectors. And being built right now is a detector in Japan inside the same mine that did the detection of the neutrinos. That's inside of a mountain. And that will be ready sometime in the next few years. And then there's a detector being built, just starting now, in India, which is going to be ready sort of in the middle of 2005. Now you ask yourself, why do you need all those detectors? And you'll see when I get further into this talk, we need those detectors to be able to determine where the gravitational waves are that come to us and where they are in the sky. I'll describe that better in a few minutes. So with more detectors, you can do better with finding out where the sources are in the sky and then being able to relate them to things that you could see with a real telescope. And that's very important in this whole science. So I'll give you a quick movie of LIGO. This is a very quick tour. This is LIGO looking at it, down on it in Louisiana. And if this movie runs, yeah, I hope it runs. Yeah, that's LIGO looking down on it in Hanford. And that's a big tube of concrete that protects the thing. Has the same kind of tube that protects the thing down in Louisiana. And these are the tubes themselves that have a very good vacuum in them, and the laser beam runs back and forth in this. You have places I've seen this morning that look just like this. These are laser tables where people set up the detectors. And this is the control room in Louisiana, and people learning how to run the instrument. So you got a quick tour there. Okay. Now, this picture, I do just want to say what it is because it tells a story. I didn't show you all the makings of it, but I'll tell you what this one is. This is the progress that we made in the time from 2001 when we started building in the field to about 2006. And this is frequency. Here is about 100 hertz. That's sort of here's middle C on the piano. It's right about there. 256 is right about there. This is a kilohertz. These are frequencies of gravitational waves, and this is the amplitude of the displacement we might measure. This gets smaller and smaller as you go down. These are all logarithmic. I'm not going to tell you any more than this, but I want to show you something that's quite obvious, that as time goes on, and these are different years, we got better and better at it. The first detector we built was up in here, then we improved it a little bit, and then we improved it some more, and then we improved it some more, and then we improved it some more, and finally we got down to here, and this is buried in here is the design sensitivity for that detector. You see that dashed line in there? That's the design sensitivity. We didn't quite make it at very low frequencies, but about above 60 hertz, the design and what we got able to do worked pretty well. And because of that, we did two things. We made a clean, non-detection. And you'll say, what in hell is good that? There's no good in that. Yes, there's a lot of good in that. It says we understood what made that spectrum. We understood why it didn't go any better than that. And so consequently, and we also can say any data you look at from that time, and there's data on the web, if you want to look at that data, that has no gravitational waves in it, that, as best as we can tell. And that gave us now the ammunition that we could go back to our funding agents and say, we built this, we see nothing, we see a good, clean nothing. Please give us the money to make something we can see. Okay? And they were sweet enough to do it. You as taxpayers helped them, okay? And we built things which I will only describe, which were the big changes that were made that actually allowed us to make the detection. And what were they? They were working on the other thing that Kip challenged us to. Namely, we had worked to make the interferometer so it was sensitive enough so you could measure a position as small as 10 to the minus 18 meters. That was the first effort. But the next one, we didn't have enough isolation from all the things that were shaking the mirrors around. That we knew. We were hoping for the best, but this turned out to be a very hard job. And so we did several things. One of the things we did is we built something called a multiple pendulum suspension. And let me tell you a little about how a pendulum helps you isolate the ground noise. I could do it by taking my belt off, but I don't think I better do that. The thing is, my right hand, this hand up here, is let that be the ground, and let my left hand be the actual mirror. And if you move the ground very slowly, these two things will move together. And you can try that at home with a string and some weights together. You just try it. And now, if you move this fast, quickly, faster than the period of the pendulum, this won't move much at all. And that's the isolator you want. You want to isolate the ground motion from that mass. And that's done with a vengeance here. It's done, here's the ground is attached to these springs. There's the first pendulum. That pendulum is hung from another pendulum. That pendulum is hung from another one. And finally, here's that precious mirror that we have to protect from all the things but gravitational waves. So that was the first step we had to take. And you'll see this mounted on a gadget, which I'll only tell you about. That gadget is too complicated to explain to you here. You can ask me about it later. But you can see this gadget, this pendulum, all four of them hanging from it. Now, what is that? I'll just tell you in words what that is, because you have experience with this. You don't know it. How many of you in the audience have ever used these noise-canceling headphones in an airplane? Oh, a good number of you. Do you know how they work? Well, I'll tell you how they work. The way they work is you have a little microphone that's outside the headphones, and that picks up the noise. But remember, you're listening to music on the inside, and the headphone has little drivers inside, and it takes some signal from the outside, inverts it, and drives the same headphone drivers as the music that you're listening to, thereby canceling the noise of the airplane or whatever you're on by using the signal that you pick up on the outside of the system, away from your head, using that as a way of getting a measure of how bad the noise will be inside your headphones. And they work very well. I'm always impressed how well they work. This idea is exactly the same idea. What you do here is you have a seismometer, which is a device that measures your motion with respect to the fixed stars. That's your sensor. And then there's pushers that push a platform around to cancel the signal in the seismometer. You force a platform to go exactly opposite to the direction the ground wants to move it. And you cancel the motion. Now, you can only do so well, so you do that twice. There are two seismometers here. Actually, this slide doesn't show everything. But this is called an active vibration isolation system. And it's something that, by the way, those of you who do very precision measurements, like, for example, trying to make semiconductor lithography or microscopy, and you live in a building that's shaking too much, you might want to call people in LIGO, because this might be useful to you. That's one of the things we can export. Okay, so there it is. And what did we see? Well, we saw this. Now we have a new detector with all these new things to reduce the stochastic forces, as they're called. And we saw the following. This is time. I'll be a little more careful here because I want you to understand this. This is time, and here is the strain. And you'll notice that the exponent here is 10 to the minus 21. You may not be able to see it, I'm telling you. 10 to the minus 21. And here is something which eventually has a signal. This is junk. And this happens to be in Livingston, in Louisiana. It's junk. And then there's something that comes out of the junk. And then it does this, and it looks kind of clean. And this is junk again. I wish it weren't junk, but it's junk. And here's the same signal seen at Hanford. There's the junk, noise. And then something comes out of the noise. Not too different than that, and again, that's noise. So let me show you what they look like on top of each other. They look like that, and you can see the whole story now. You can see the junk doesn't correlate, but the place where there's something that is coming out of the noise, they are not exactly the same, but close to the same. And what has been done to do this, you've taken the signal from Louisiana and shifted it by 7,000th of a second so that it stands on top of the other signal. That tells you something right away. The signal got to Louisiana first, and then it got to Washington. So it got there first, went through the Earth, came up and when you put them together, you have to slide them so that they are really on top of each other. Okay, so now let me show you another way to look at this signal, because we'll need that for something in a minute. Another way to look at that signal is to look at the frequencies that are in that signal. So now, what you'll see here, this is again data from Hanford, data from Livingston. This is time again on this axis. And here now it's not strain anymore, it's the frequency represented by that waveform. What's in there? You make that waveform up out of all different sine waves. And here are the different frequencies associated with it. And here is the strength. The brighter something is in this picture, that tells you the frequency that you need to make that signal. And those of you who know what Fourier transformation is, this is what that is. And so what you've made a sonogram of what that signal is. And so, for example, you'll see here's middle C right there again. And that signal is about as strong as you can get. The brightness tells you the strength. It's probably strongest at about 150 hertz. Here's the same thing, a little better, at Hanford. Hanford was a slightly better detector at that time. And now, and I want you to hear it. So this is what that sounds like. And let's see if I can make that happen. That ain't much. Bloop, bloop, like that. Okay, so we'll do it again, and now we're going to pull a trick on you. I'll change the frequency content of this so it's better in your ears. Okay? So that's a chirp. Okay? And that was a big deal, that chirp. So anyway, what is that chirp? And here comes the other miracle besides the detector. And I told this to Richard Matzner today. This is a miracle also. What you're going to see now is a computer program that took years and years to develop. Some of it here, some places, some in other places, of using numerical methods to solve the Einstein equations. Those very difficult equations to solve. It took many years to do that. And it turns out it's sort of interesting. Almost the discovery of the gravitational waves was almost simultaneous. On a time scale of Einstein, it was certainly simultaneous. Within a couple of years of each other, the people who had been working on numerical relativity were able to get results from that for a whole set of problems that probably were the source that we're seeing. Two black holes, and we'll show you that. Two black holes going around each other, and you'll see what that movie, generated by a computer, not by an artist, looks like. And so what we're going to now do is you're going to see the waveform. I don't know if you can see it. The waveform is down here. You're going to see what's going on in the system. And by the way, again, the way you want to think about it is that jungle gym. You're taking a cut, and we'll talk more about that, across a two-dimensional cut across it. But now we have a way of representing the time as well. So let me get started. And here is what actually is the best fit that we have to what these waveforms are these two black holes going around each other. There's the time up here. And now you have a couple of things to look for. The colors in here determine how the clocks go. The darker they become, the slower the clocks are going. And then these little arrows are the distortions, effectively the strain in the space, in this two-dimensional cut through the thing. And so consequently, you'll see that these are, now the waveform is, you see where we are, we're about there. Our waveform sort of began right about there someplace. And these guys are going to get faster and faster, closer and closer. These holes are going to get deeper and deeper. The clocks are going to go slower and slower. And yeah, well, there's a place now. Now they slowed the movie down. And here, it's still, the clocks have stopped right there. Just come to a dead stop. And now you can see these two making a real storm in space. I mean, this is a gigantic storm. And then they make a new black hole, and that's it. That's what people thought, and were right about when we discovered these waveforms. And without numerical relativity, we couldn't have solved the whole problem. People could do it you could do it analytically for much of it, but not all the way. So that was a big deal, and that all came together about the right time in the history of science. It was wonderful. And here's what happened to me when I was going. This is shortly after we made the announcement in Washington. I was on the subway in New York going from Manhattan to Brooklyn, and I saw this advertisement on the wall, and I'll try to read it to you. Scientists found gravitational waves in outer space. If only were that easy to find an apartment in New York City with a walk-in closet. Now imagine, this is only a couple of days or maybe a week after the announcement of the discovery. Somehow it hit the public conscience in a remarkable way. And then this cartoon that comes out of the New Yorker, it's February 12th, and it says, two birds sitting next to each other, a guy on the outside there saying, was that you I heard just now, or was it two black holes colliding? See that chirp, that chirp that you heard. Well, anyway, I mean, to get into the public conscience so easily is sort of amazing. I mean, imagine the Higgs boson being explained so easily, okay? This Einstein, whenever I go to grade schools, I always ask the kids, name a scientist, and they always say Einstein, okay? And I tell them about black holes, and they say, we know all about those. They're terrible. You don't want to go near them, So, I mean, they know, they don't really know, but they know. So you're not having to explain a language. It's a very different kind of thing than explaining something really complicated in physics. This was amenable. Okay, well then what happened, very good to us, thank God, was that this is now the same picture, but a little more of them. This is time again, and now a whole bunch of these. And this is, what is the designation here is, that's the year 2015, that's September 09, and the 14th of September, and that's the thing we've been talking about. Well, a little bit later we saw, and that's now to October, we saw this, we weren't sure of this one, so we called it an LV, not a GW. Then we saw this thing at about Christmas time, and that did it for me. I mean, this is now, and what's associated with these things are the different masses you can see. That, I can't read them from here so easily, but 36 solar masses, 29, 3 solar masses in this system disappeared off as gravitational waves. That's an interesting story, and we'll talk about that later if you want. What would happen if this was happening at the position of our sun? I'm not going to go into it now, but if you want, ask me about it. So this is the one that finally convinced me that we probably had something that we ought to believe in. And then there were more, and there have been more since. And we now have something like 9 of these, and now we have some more with the run which just started. And so the important next event was when Virgo, with a 3-kilometer detector in Italy, also saw this. And this is in 2017. And the important picture here, it's the same, you're now used to these pictures. This wasn't the best detection we had, but it was enough so that you could believe in it. And the Virgo people, which are not quite as sensitive as LIGO, did see it. And here is the waveform they thought. But the more important thing is now you had Hanford, Louisiana, and Pisa showing it. And here is sort of the most important picture of this slide, is here's a sky map of where you would think, if LIGO was the only thing seeing it, this is a map of the sky, and that yellow banana right there is a huge area, about 1,000 square degrees. We have uncertainty in where this black hole took place. That collision of the 2 black holes took place. Now, if you add Virgo to this, and you get this little green spot right there. And that little green spot is only about 30 square degrees. Now, most astronomers will throw you out the door if you come to them with a picture like that. Go find something that is 1,000 square degrees, and they'll laugh you off. They don't quite laugh you off if you give them 30 degrees. They still don't like that. You know, the moon is only half of the square, is 1/4 of a square degree. And they can barely, in most telescopes, get the whole moon. So in order to tell astronomers where to go look for this, which is something we dearly want to know because it'll tell us a lot more about what's going on, you have to be able to do better. And that's the reason we're building so many more detectors, we hope. Now, the next spectacular event was this one. And it happened in the same year and almost within 3 weeks of each other. We knew Virgo was working now, and now we saw something completely different. And what we saw was something, now that you know a little bit about how to read these things, here is time, and here is frequency. This is now a sonogram of what we saw, and it goes on like this. You can see this lasts for a very long time, 10 seconds within our band, and it goes whoop, you'll hear it in a second, and then it goes and they crash into each other. Let me play it for you. It's a completely different signal. And let's hope I can do it. This thing will allow me that. Yeah, it looks like it might. Okay? That's a real chirp. It's like a glissando on the piano. You go like that with your fingers. And, well, the thing that was so marvelous about this was that here is what was seen by an X-ray satellite, the Fermi satellite, and we think at the moment when this happened, when they collided, we didn't see the very end of the collision. That's at higher frequencies than we have good sensitivity for, but we think we know where it happened. It's that line, that vertical line. And here is the Fermi satellite that saw a gamma ray burst, which was not super big, but certainly outside their noise. There it is. And that difference in time is about 1.7 seconds. So, and here is another instrument on that same satellite that also saw something. And here is something not so good signal and noise that saw a different satellite. So finally, a most amazing thing happened. We had confirmation of an electromagnetic event that was associated with our event, which we knew what it was. We knew that was the collision of 2 neutron stars. The same thing I told you about earlier in the talk that Holt and Taylor had found by their radio telescope. Not the same place, a different one, 130 million light years away from us. But the important thing, it told us something right away. It told us that the gamma ray signal, which is electromagnetic, and the gravitational wave signal traveled from that source, which is 130 million light years away. They traveled together for 130 million years and got to the Earth within about 2 seconds of each other. Well, that doesn't tell you nothing. That tells you that those two things were moving, those two signals were moving at the same velocity, to apart in 10 to the 15. So we now know for certain that that gravitational waves move at the velocity of light, and that eliminates a whole set of theories, by the way, which were never good theories anyway. But I hope I'm not injuring any theorist in the room, but there were several theories that predicted that gravitational waves would travel at a different velocity than the velocity of light. It's no longer viable. But a lot of other stuff was discovered also. And here is the thing that then made what we now call multi-messenger astronomy. And that's a buzzword that actually is a pretty interesting buzzword. So here is, again, a sky picture. And that sky picture has the uncertainty from LIGO, these bananas, right? That banana and that banana. And then because Virgo, I'll be honest with you, did not see it. Virgo did not see it, but it should have seen it. And that told us that it was in a zone of silence, that it's 45 degrees to the plane of the antenna Virgo, where Virgo is. That piece of knowledge, by Virgo not seeing it and should have seen it, puts it in this little pattern right in here. And here's where Fermi, the satellite, thought it was. That's not very good. And the two instruments. So the fact that we were able to localize with the non-detection in Virgo and the detection in LIGO, we were able to localize it to there, enabled the astronomers on the ground to look at a galaxy, this galaxy. But they had looked at it, luckily, some 20 days before. There's the galaxy. And those stars are in our own galaxy. But that's that distant galaxy smeared out like that. That's what galaxies look like in these pictures. And there's that same picture about some number of hours after I can't read it, 10 hours after. Here's that galaxy. There are the stars that are the same down there. And there's a new thing which has never been there before. And that is that neutron star collision. And boy, was that exciting, because 300 telescopes on the Earth with all different wavelengths trained in on that. They were able to go to it, and they found out that it was indeed, this picture is what the idea was. Here are the two neutron stars, and they're coming together. They're going to smash into each other. Eventually, they make a black hole. It's too much for the nuclear matter to hold apart. And there's a gamma ray burst. It's a weaker one. It's not directly on axis. And in here is this big mess of nuclear neutrons and a little bit of protons, and it makes new matter. And that solved another puzzle which a lot of people had worried about, which is how do you make all the elements that we live with? And I'll spend a little time on that so that you are with me. It turns out that, let's talk a little bit about what we know about where the elements are made. And you see chemistry and physics are the same, okay? Don't think they're different. So this is the Mendeleev table, the periodic table. And there's a color coding in this table, which is actually kind of neat. Where it's blue, the particular element was made in the actual explosion that made the universe. Where it's yellow, these elements were made most likely in stars where they sat there and cooked away for a long time of the life of a star and then got thrown into the medium, of the interstellar medium, by a supernova. Or they just actually they're made, green is also very similar, they're made in all sorts of stars. So you can see what happens. You can see that you can get some way, you get helium with the initial explosion of the universe. You can go all the way over here to helium, and you get that. And those are the two really blue ones. There's a little tiny blue band on lithium that has mass 3, and you can't see it, but there's a tiny little amount made of beryllium. And then you get stuck. You can't make anything else. Boron, you can't make at all. You can forget about it. And that's something that George Gamow and the people around him knew in the 40s already, that you couldn't make anything heavy in the Big Bang. So you can make it in stars, and let's see what's made in stars. All this stuff that's yellow and green. But how far do you get? Well, here's stuff that we don't get in stars, like gold and platinum. Gold and platinum, not made in stars. Where's it made? And that was always a big question. Now, people had guessed that it was made in these neutron star collisions, but this was first sort of proof. Now, I'm a little disappointed in the proof, just so you know. The proof was actually looking at, with infrared light and all the different colors of infrared and visible light and UV, radio and X-rays, all techniques were used. But the thing that really would have identified these elements would have been the optical. And the optical, you could not actually get lines that said, here's a gold line, and there is a platinum line, and compare it to a line that's generated in the lab. The reason you can't do that is these things are moving, these stars are moving almost at the velocity of light when they crash into each other, and they're moving at an incredible velocity. So the lines get smeared out all over the place. So you have to do averaging over many, many spectral lines. And some very clever people have done that, both at Los Alamos and also in the universities. And they came up with that the way the colors changed as a function of time, that the observers saw, matched how the radioactivity in that cloud changed with time. And so that's the best we have. We didn't see individual lines, and that may never happen. But so it's 90%. I still hold out 10% that I wish we had another way to show this. But most people now believe that this process of neutrons attaching themselves to heavier things is the way we get all the heavy things. And of course, these here are made by man. That's something else. So all the heavy stuff, including the stuff we love to have, is made in these neutron star collisions. A big discovery. And I don't think I want to go into this. This is just another way of measuring the universe. Ask me about it in the questions. I do want to say something else before we end. This slide and one more, so have patience with me. This is sort of the direction of this is more for the experts in the audience. There are a few. This is sort of what I consider, and we are now beginning to consider, the progression this field will make as time goes on now. And what you're seeing in this picture on the left, is the spectra, the strain spectra of a set of detectors. Here's 100 hertz, and this is 1,000 hertz, and these are associated with different things we do in LIGO and also in other detectors. But where we were before the detection was made, we were up here. We're going to have, when we finally get done with advanced LIGO, we hope to make another factor of about 5 improvement, and we're now running, and we've gone about halfway to that. Then there is another project that's going to be operating in about 2025, which is called A+, which is some improvements on LIGO if we ever get to the design of advanced LIGO. And then we are thinking, if we want to go further, we're going to have to make a big jump. And that big jump is being made in Europe as well as in the United States. What's only here is the United States part. We want to build a 40-kilometer long detector, and one in 2 phases. One using the technology we now know, and another using technology which we are working on but we don't have yet in hand. And what that will do is this. This is a nice picture that tells you what this will do. This is all the black holes that we've now detected, and you can see if you build Cosmic Explorer, the red one, you will encompass this. This is the distance measured in redshift, z. So right here, you will encompass all the black holes that we know about, and any population of black holes we anticipate. And over here, you are all the neutron star binaries, at least those things we know. And even with the initial Cosmic Explorer, we don't quite get them all. That's this line right there. But if we want to get them all, we have to go the next step to do that. So in other words, what does this mean? If we can get to this point here, we can finally get into what's called the science of the universe in its entirety. That's called cosmology. And that would be a wonderful thing to be able to do with this new way of looking at the universe. So here's my last slide. Now I want to tell you what's going on all in the world around you right now in this field. And it's not just LIGO. So what this is a picture of is frequency of the gravitational waves. So here is 10 to the minus 16 hertz. There's 10 to the 4 hertz. Or up here are the times, 1/10 of a second to 1,000th of a second. There's sort of this little band. And here's hours to minutes, years, finally age of the universe. That sort of and here are different strain values that different technologies will do. And here's LIGO. We've done a lot of talking about LIGO. I don't want to say any more about LIGO. But here's something I haven't said a word about, which is if you want to look for gravitational waves at periods of hours to minutes, there's a very elegant project that's about as old as LIGO, but that's going to be done in space. And the idea is to mount 3 satellites in an equilateral triangle, put them in orbit of the Earth at the distance of the sun. And if the sun is there, that's the orbit of the Earth around the sun, and it's behind us in the orbit. And that triangle turns out to have some very beautiful properties. It's stable, and it doesn't need much station keeping. And with that, you can now then measure, for example, black holes of the kind that are the things falling into the black hole in the center of our galaxy. And big black holes. You'll also see white dwarf stars, a whole bunch of stars in our own galaxy, all with very much longer periods. Fascinating stuff. And you probably can do the best tests of general relativity using the big black holes and small things falling into them. That project will probably fly. It's no longer just America. Not that I want it to be, but the Americans gave up on it, and the Europeans picked it up. Americans are trying to buy their way back in, which I hope they do. But this will be a European mission, and it's called LISA, the Laser Interferometer Space Antenna. It was invented in the United States. This is a project that's now going on, and this is called pulsar timing. And the idea is a charming idea. It's using radio telescopes, listening to these pulsars, and the idea is to look for something really quite elegant. Suppose a gravitation, here's the plane of the galaxy, okay? And suppose gravitational waves are coming in, and they're coming in very slowly. I mean, they're moving at the velocity of light, but you're looking at something coming into our galaxy. And so that takes 10,000 years to go across the galaxy, okay? So what happens is you look at pulsars, and you look at pulsars in the northern part of the galaxy, and suppose they speed up a little bit because the gravitational wave is coming through. So those guys speed up. Down in the south of the galaxy, those speed up also. But the ones in the left or the east side of the galaxy, they slow down. And the ones on the west side of the galaxy, they slow down. So you look in your radio telescope for a signature that has pulsars going faster in opposite directions, and slow, and well, in north and south, or however, and going slower in east and west, or the other way around. Just differences that are this quadrupolar-like pattern. And that's what they're looking for. And they can detect black holes colliding with each other, hopefully, that are in galaxies. Huge black holes, 10 to the 11 solar mass black holes in early galaxies. That's one of them. They're hoping to look for a background of gravitational waves. And this has been going on. They haven't detected anything yet. They will do better if they have more pulsars to look at. And that will be a big step forward for them when they get a new telescope called LSST, which is a telescope that looks for transients all over the universe. And that'll be ready sometime in the next 5 years. And then there is something which had made news. It turns out, unfortunately, they were wrong, but the idea is still very, very good. And the idea here is something really this is the most grandiose of all the ideas I'm going to talk about. This idea was, and they tried this, there was an announcement made about 3 years ago that they had discovered what I'm about to tell you. It turns out people had another look at that, and they found out that no, it had not been discovered. They were seeing dust in our own galaxy. But what were they looking for? Okay, that's a little bit of a story. You have to know a little bit that the universe now is radiating at every part of the universe that you're looking at. Looks like it's a black body, that's a Planckian black body at 3 degrees Kelvin. That was discovered in 1965, 1966. That cosmic background radiation is the residual amount of radiation left over from the explosion that made the whole universe. It's a fantastic idea, and it has stuck. It has worked every time you test anything about it. Its distribution in space, the spectrum, the distribution of galaxies, everything you can test looks like it's right. The idea that the universe started as a point someplace, expanded, and then now it's quiescent, it's still expanding, but it has a temperature of 3 degrees Kelvin. So now it turns out that's electromagnetic radiation that's being radiated. Had there been, before the explosion had settled down so it was at 3 degrees, very early in the explosion, really quite close to the beginning of it, there is ideas that maybe quantum theory comes into that, and you may have had quantum fluctuations of the geometry and the time, the four-dimensional geometry of the initial universe, because the universe was small enough, so it had to obey quantum theory. And if that was true, that's called inflation, that thing I'm about to tell you, and many of you have heard of this. What happens is there may very well be gravitational waves that were generated by quantum fluctuations in the very earliest moments of the universe. Those gravitational waves may then cause things in the plasma that we now see the 3 degrees from. The 3 degrees Kelvin is generated by the plasma that remains from that initial explosion. And if you can have in it regions where there are hot spots, in 2 hot spots and a cold spot, generated by the gravitational waves that were preceded all of this, you would see a polarization. You would see the electric field have a particular direction of the cosmic background radiation, would have a particular polarization. That electric field in that cosmic light. And that would have a very special pattern. It would look like a pinwheel going around. And people had started looking for that by looking at the polarization of the cosmic background. And they did that back in the South Pole. They thought they saw something. It turned out what they saw was actually magnetic fields in our own galaxy orienting dust, so the radiation got polarized. But that didn't scotch the experiment. They only had one wavelength to look at, and so they couldn't separate the dust from other things. Now, that experiment is being done both in Chile in the Atacama Desert. It's also being done at the South Pole. It's being done by the Chinese in Tibet. It's being done all over the world. And I don't know if they'll detect something, but there will be a result that we can believe within the next 5 years. And that would be most spectacular if they see something. So thank you. All right. Somebody's going to help with questions. I'm willing to answer any questions. I mean, as crazier ones, all the better. Okay, good. So let's start with somebody right there. You do the pointing. Can you see the people better? Yeah. Okay.
You skipped over a slide talking about all the different sources of noise that there were when you were developing the interferometer. What are some of the more subtle ones that affected its performance?
I couldn't get. Can you get closer to the mic somehow? What?
Sure.
Yeah, go again. Say it again.
Sure. What were some of the subtle sources of noise in LIGO, and how did you deal with them?
Okay. Well, that was the slide I left out. You want to see that? Is that the point? Okay, let's quickly go there. But you know, you're on your own time now. Okay? Anybody who wants to leave is welcome to leave. Okay? So let me go back to that slide. And that actually looks at some of the noise. Now, I won't go through all of it. Go a couple of them. There's a lot of explanation that goes with that slide. This slide is the one you're talking about. Yeah. So the big noise, what this is a picture of is the strain as noise, and this is 10 to the minus 23 per root hertz. In other words, per unit bandwidth. And this is frequency. So here is 10 hertz, 100 hertz, 1,000 hertz, 10,000 hertz. And this is the envelope of the initial LIGO detector, the one that didn't see anything. Okay? And you can see what limits it. What limits it down here is the shot noise, which is the quantum noise of the radiation field that comes in as vacuum fluctuations from the vacuum fields. I hate to say it, sounds very theoretical, but it turns out we now know that shot noise comes from fluctuations of the radiation field due to the quantum theory of the radiation field. And it comes in the anisymmetric port, comes in where the detector is. So that's shot noise. You can also think of it in counting statistics, but that's the wrong way to think about it here. So that's the limit. If we have more power in the laser, that pushes that down. Okay? That quantum noise extends over here, which didn't bother us. That now begins to bother us in the new detector. Here's radiation pressure noise. And what is that? That's noise that has to do with that the light is actually made of photons. And the light, when it hits the mirror, the photons make like a hail on the roof. And it pushes on the mirror. So it's very much, I don't know, have you studied quantum theory yet a little bit? It's very much like the Heisenberg microscope. In other words, when you try to pin down where an electron is and you send light on it, if you want to tell better and better where it is, you want to use shorter and shorter wavelength light, which means it has more and more momentum. And that momentum kicks the particle. So this is the noise that comes from that you don't have enough, the wavelength is too big. And this is noise that comes about because you don't have enough, you have, the photons are kicking the mass around. That's called the quantum noise. And so you can see the outline of the very first detector. Now this bothers us, but that didn't bother us. Now here's the other thing that limits it, that's thermal noise. And that's the fact that everything at room temperature, these are all at room temperature, everything at room temperature is shaking a little bit. That's called Brownian motion. And Brown saw that first under a microscope. The biologists know all about that. And everything is jiggling a little bit because it's at room temperature. So that the mirrors and everything jiggles. And then finally here, the remaining noise was seismic noise, the noise of the ground, shaking everything. And we didn't have a very good isolation system. That's why we built a much better isolation system. Let me show you one more noise, which is fundamental, which is very serious. And that's this noise right there. It's not yet a problem in this detector. It becomes a problem in all subsequent detectors. This noise, which is coming up like 1 over the frequency to the 8th power, some huge factor, is the following. It's something you can't do a damn thing about. And it's the reason why you want to go into space, to make a detector that low frequency. I'll tell you what it is. It's pretty straightforward. Here, you can always tell, you can get rid of the seismic noise because you can make it a seismometer and measure it, and then kill it by this technique I told you about. But you can't do the following. Here's the ground shaking, and the ground has compressive waves in it that travel, compression waves. And let's say our mirror is right there, and here's a wave that's compressing. And what happens all of a sudden, here's that mirror, there's a higher density of stuff right there. So there's more mass there than it was before. And that mirror gets sucked over by just Mr. Newton. That F equals G times M1 times M2 to by R squared. That gets pulled over to the ground, and so that, you can't shield that. You can't put anything in the way. You're stuck. And the same thing happens in the atmosphere. The atmosphere has density fluctuations that move by the detector. and they move the mirror around. And that's what's called gravity gradient noise. And that kills the thing by the time you get to about 1 hertz. You just can't deal with it. And that's why people want to go into space for low-frequency detectors. Okay? Thanks for the question. Yeah.
We're gonna,
Hey, you better, you do the talking.
My question is kind of humorous, if you have more business with humor. When will you think the world will end?
I can't hear you. Can you hear? Can you hear?
she said, when do you think the world?
When will the world end? How would it end? And why would it end?
Okay, tell me what.
She said, when do you think the world will end? Why do you think it'll end?
Oh my God! Did I say the world will end? I don't think the world will end, but we got to tend to the problems we have, right? I mean, gravitational waves are not going to save the world either. No, what's going to save the world is a little intelligence and how you deal with the environment, okay? And how you deal with human misbehavior. I don't know. We have to solve that. I don't have any better answer. I'm sorry.
My question is, to detect the gravity wave, you're basically detecting degrees, small movement in the mirror. Does the mirror then rebound, or is it permanently moved or distorted by the gravity wave? In other words, does it pulse, or is that a permanent movement or shift in space-time?
Yeah. Let me tell you, you asked the hardest question that almost made this field go to hell, okay? The question he's asking, let me paraphrase it, do you mind? Is that, I'll make it a conundrum, which makes it even harder, okay? The conundrum that this field was up against in the early days was the Weber bars didn't have that problem. By the way, now you know what the Weber bars were, as I said, 1,000,000 times less sensitive than what you needed. But we were troubled by a different problem, which was the problem that people misunderstood how you use the general theory of relativity to make a prediction for how much motion there is at the end masses, or if you want to even think of it as a motion. And the trouble is, and Richard Mattson will tell you better than I can, that there's this business in the theory that there is freedom of coordinates. You can use any coordinate system you want, but that doesn't mean that when you change a coordinate, or a coordinate changes, that's something that's measurable. You have to do something much more special in this theory to prove that the thing that's wiggling is measurable. And so let me give you what caused the trouble. I'll draw you right into it. If you're not careful, and this is what people did in the early days of this, they said, oh, okay, space expands and contracts like what you show, but you know, why doesn't the wavelength of light expand and contract along with it? And you won't measure a goddamn thing. And that was all over the place. I mean, people who had been making bars, people who were theorists, and they killed this thing for a long time. You had to answer that question. And the question was an ill-posed question because it mixed gauges. That's the trouble, if you want to know. So one way to think about it that doesn't get you into trouble is just forget about the wavelength. Use clocks all in one place, okay? And just say, measure the time it takes light to go from A to B and back again to the same clock. No, don't worry about transferring the time. It's all here. And then also do the same measurement in the other direction, okay? And see, are the times the same still? And you don't talk about wavelength at all, because the clocks, they tell you what's going on. That's a neat way to say it, but it evades the question a little bit. And another way to think about it, which is a more modern way to think about it, and I'm giving you all the different ways, is that to think, and this is an engineering way of thinking about it, but one I like the best, is it turns out if you solve Maxwell's equations, the equations of electromagnetism, in a gravitational wave, you can solve that. You know how to do that. Einstein told you how to do it. You take that, write it over in a tensor form, write it in, and write down how the metric changes due to the gravitational wave, and carry it through, just carry it all the way through. You'll find a very interesting thing out. You'll find out that sidebands are put on the electromagnetic wave by the gravitational wave. In other words, the electromagnetic wave might have a single frequency, and after it has come through the gravitational wave, there are phase-modulated sidebands at a frequency that's the gravitational wave frequency below the carrier frequency and another one above the carrier frequency. And that is stuck to the light wave. Nobody can argue with it. Any person who has a spectrum analyzer can go measure that for him or herself. So there's no question anymore. What coordinate system you're in? It's a real effect that's made on the light due to the gravitational wave. I choose to think that that's the way to get around this whole problem.
Has that been detected?
What?
Has that been detected?
We detect it every day. That's another way to look at this whole problem. Yeah. Thank you. Thank you for the question.
I have a question. Earlier you talked about how detection of gravitational waves lined up with detection of a gamma ray burst
Yeah.
with a 2-second difference. And I was curious as to where that 2-second difference comes from, if it's a difference in time of the events themselves at the site of the collision, or if that's a difference in how they travel through space.
Well, I think I understood your question. I mean, you're asking why is it different by 2 seconds? Is that the worry?
Right.
Yeah, okay. Well, okay. Look, forgive the 2 seconds, okay? It's a part in 10 to the 15, okay? Those 2 seconds. But even so, it's not so hard to imagine when we will learn more about this, when we see more of these, that it takes a couple of seconds for the electromagnetic radiation to actually form. The gravitational waves come from only the acceleration of the masses, and they smash into each other, and that's when the big end comes, okay? And you see that, and there's no chemistry involved. There's no delay time in that, short of what is the radiation lengths within the gravitational wave paths themselves. On the other hand, it takes a while. For example, as these neutron balls fly into each other, it takes a while for all of them to get together. It takes a while for the chemistry, the nuclear chemistry to take place, the neutrons to find their protons. That could easily take 2 seconds when you think about it. So somebody will solve that out, and I bet you the 2 seconds will disappear. That's my guess.
Thank you.
Okay, yeah.
I refer to the very end of your lecture. If I understood this correctly, and I may be all much stuff, but I understand that at the very, very beginning of the universe, there might have been gravity waves in the process that right now we don't have the proper instrumentation to be able to detect because there may be a different kind of gravity wave. If we develop the instrumentation to eventually detect these early gravity waves, would that be an indication of where the Big Bang may have started?
Okay, all right. Okay. Let me answer your question. First of all, let me dispel something. First of all, he's asked a very interesting question. He's asked 2 questions. One is, how could we ever actually detect with the instruments we make that primordial gravitational waves? That's one question you're asking. The other question is there a center? And there I have to argue with you, okay? And that's an important thing. It turns out that if you have to think about the universe as that there is no center. I'm sorry, you have to think of it, and I'll give you a way that you can do this for yourself at home, okay? Some people like to think of the universe as a big rice pudding. Okay, you know, that's an idea that you read British Bondi's book, for example, on cosmology. You think of, put raisins in a big pudding, and you put them all over the thing, and then you put the thing in the oven, and then you start, you have yeast in there, and it starts growing in all directions. There is no center to that. And that's sort of the way you want to look at the universe. And the way you can draw yourself a picture that will prove this to you is assume that what people did in the beginning, it's not completely right for the very edges, but it works beautifully for the middle. And that is, think of that everything is moving away from everything else proportional to the distance they're away from each other. In other words, here we are on the Earth and we see a distant galaxy and we know the distance to it by various means, and it's moving a certain rate away from us, okay? But it's linear. The amount it moves is proportional to the separation of the Earth from that. Then you go out to a further place, and you find that the velocity is larger. And if it's twice as far away, it'll be moving twice as fast. With that linearity law, which we measure directly for nearby things, you can then put yourself at that galaxy, the one that you saw, the first galaxy you looked at. Plunk yourself over there and look at the Earth. And it looks like it's moving away from you by 1 unit, and you look at that other galaxy and it's still moving away from you by 1 unit. So there is no center to that problem. And I want you to think that way, okay? It's not easy to do that, but that you need to think that way. There is no center to this. And what happened is, as the universe unfolded all around us, around every place in the universe, what happened is in the beginning it was very, very dense. Light was everywhere. You got blinded. And everywhere in the universe simultaneously, very far from us and very close to us, the universe became transparent. And that's what happened at the time when that cosmic background radiation was generated. Now, let me get to the instruments, okay? This instrument will, I hope, detect something. Right now, it's still extremely speculative. There are theories out there that say there are no gravitational waves from a primordial source. And right now, in order to do this experiment, you can't, LISA won't do it, LISA won't measure it, LIGO won't measure it, it's not sensitive enough, LISA won't measure it, but you can design an experiment now. It's called the Big Bang Observer. You can look it up on the web if you want. That is effectively taking the technology we have developed on the ground, not the LISA technology, the ground-based technology, and putting it in space. That's all those high-power lasers and all this incredible technology. Stick it out there over lengths that are millions of kilometers. And when you do that, you can get numbers that get you about a sensitivity that's almost good enough. But nobody at NASA will consider this until you have shown that there's something worth doing. This is a terribly hard experiment to do. Take LIGO and stick it in space. See, putting LISA in space isn't the same as putting LIGO in space. It's a very different technology. So, yes, one can think of it, but it's, I think, 50 years away. Okay? That took a long time to explain, but okay. Thank you for the question. Yeah.
We don't
My
have
question
What?
is,
We don't have time for another question.
Okay. Well, you claim we don't have time for another question. You want to call it off? One more?
Okay, we'll do
One more. But then help me understand this. Okay, one more. Over there?
yeah. So my question is, considering any directional properties that scientists have been able to measure with respect to gravitational waves, have we been able to define those properties in relation to the direction of the expansion of the universe?
Okay, wow. Right now I failed to mention something to you, which I should have told you. There are polarizations of the gravitational wave, so you don't leave this place with thinking it's only as simple as the little picture I showed you. The picture I showed you had things going like that, up and down, and stretching going up and down, and east and west. It turns out you can take that picture and turn it by 45 degrees, and that's another polarization of gravitational waves. Okay? Now, the reason I bring that up is that there are ideas around that if the universe expands non-symmetrically, which I don't think it does, we have pretty good evidence that it does, that the polarization patterns will be different from sources in different places. I don't believe that, but that's been written up, and you're welcome to have it. I don't know how else the universe gets into the propagation of gravitational waves except in one other way. And that one I'm sure does happen, is that we now, when we look very far away, we see lensing of all the stars and galaxies. In other words, a very distant galaxy, we might see multiple images of one distant galaxy because the light from that galaxy has gone through other light, a matter that was in front of it, between us and it was bent by the matter in that galaxy. So you will get multiple images. These are not wonderful lenses. A galaxy that's in the way has the property of making little spot images. And that will also happen to gravitational waves. They'll get bent by intervening matter. They get bent, but they don't get scattered. They get bent. And so consequently, there will be the same thing as with light. You will see very distant, for example, we'll probably see that with black holes where we get into that big detector. We'll see places where you get multiple images of the same black hole pairs when that gravitational wave comes through the galaxies between us and the black hole source. That's the best I can do for you.
And do we know whether gravitational waves can travel through black holes?
No, we know they don't come out of black holes. They fall into black holes just like everything else. Now, we know that from the modeling. Nothing comes out of a black hole.
Thank you.
Thank you. Okay, I think that's it. I'm sorry there. Yeah, thank you.